Let's start this fourth session. We're delighted to start as a keynote with Professor Tim Rogers, who is Professor of Mathematics at the University. Tim works on understanding, in particular, the behavior of complicated random processes in network and spatial structures, and focuses on understanding emergence of kind of large-scale order from these random interactions. He's published in a vast array of illustrious outlets, including the Nature journals and the Proceedings of National Academy of Sciences, amongst other journals. And he is going to talk about the speed of contagion. So, Tim, it's over to you.
Thanks very much for that invitation, and thank you for the invitation to speak. Yeah, it's a shame we're not in person, but I'm slowly getting used to these online presentations. So I'm going to tell you about some work that I've been doing actually for about 5 years now on predicting, no, seven years now, on predicting the speed of contagions in networks. Now, I want to say up front, so most of what I'm going to discuss in these slides, I'm going to use terminology about epidemics, and epidemiology is one of the important applications, but it's not the only thing that spreads in a network. And I know that there's a diverse range of interests in the audience today, and so I want to suggest 2 other applications that people might want to be thinking about while I'm talking. So one of those is information, whether that's information about indeed about an epidemic or something spreading on social media, or information about something in finance, whatever. So the way we communicate now very quickly through social media, there's a speed of information spread which is absolutely enormous, and is somehow a feature of the platform over which the information is spreading and the social network that it's embedding in. And then the other application you might want to think about is financial contagion. And I'm sure some of you have worked on this. So, you know, when one institution has some kind of event that has a knock-on effect for its trading partners or people that have a stake in it, and so on and so forth. Okay, so let me pass to this slide that I like to show. So this is a picture. I've stolen it from Wikipedia. It's a heat map showing the spread of bubonic plague across Europe. And so each of these colored bands tells you when the plague was first appeared in these parts of Europe. And you can see this kind of stripy pattern here. So there really was a geographic spread from south to north, and you could in fact measure the speed. And the speed was about 1 mile per day. And that, of course, was because the plague was transmitted by person-to-person contact, and people had to walk places, or they had to ride a horse, and they only went places that they needed to get to, and the cost of travel was slow and expensive and didn't happen very much, basically. And I'm now going to compare this to, no surprises, the obvious current situation of COVID-19. So we had this outbreak that spread extremely rapidly around the world, and did so in a non-spatial way. So it wasn't the case that we had a kind of, east to west kind of spread or something like that. It simply started appearing all over the place very rapidly. So this is a fundamentally different process, even though it's the same human-to-human interactions that are causing the spread of a disease. So that part hasn't changed. But travel has changed, right? And so because of that, the spread of this disease is vastly quicker. And in fact, can't really be measured. It doesn't make sense to measure this in miles per hour. So just to illustrate what I've just said, this is a map of the world reconstructed from airline routes. And you can make out, Central Europe and America and so on. So you can draw the world just through personal travel networks. So that's one thing that's changed. And then the other thing that's changed is our social networks. So back when bubonic plague was spreading, people lived in one village for most of their life, and they saw the same 100 people pretty much. There was none of the kind of level of mixing that modern society has. Now we have these hugely diverse social networks, and you can this famous 6 degrees of separation. You can travel around the world in a few hops in a social network. So all of this put together has created an environment where a disease, or indeed information or other things, can spread incredibly quickly. But how quickly? How can we measure this? So I've said that miles per hour is the wrong kind of units to measure this in. So what do we measure it in, and how can we go and try and make some kind of prediction? Because if you're predicting the spread of a disease in, let's say, a wild population of animals, you might be able to make some kind of prediction in miles per hour if you know about, animal movements, animal habitats and ranges, how it might spread. So how can we do the same thing for humans? And the key thing is that the network is the medium over which this contagion is spreading, and it's the network that's going to contribute some crucial factors to deciding the speed of the spread. So the work I'm going to talk about, there are 3 papers, as I said, going back 7 years. So these are the references. You can also, I've got my website link at the bottom there, so you can tap that in at some point if you want to look it up. So my 2 collaborators on this, so Reimer is at King's College London, and Sam here was a PhD student with me. He now is part of the Warwick team doing the models for SAGE, so particularly to do with the vaccination rollout. Sherry, you've got a question.
Can I just ask a quick clarification? I mean, you talk about speed in miles traveled and so on, but surely it is just time taken for numbers to double or some such, isn't it? I mean, that's also speed of contagion, how many more people are infected, or just days. Time
so I'm thinking specifically about a different measure of distance. So I'm thinking about network distance rather than, so speed usually has time and distance. So it's not just a doubling time, that would be a rate. For it to be a speed, it has to have a distance. And what's the notion of distance we want to use? And I'm going to argue that the notion of distance we should be using is network distance. And that some knowledge of the network will give you some clue as to where the infection is going to appear. Okay.
Thank you. Yeah.
Right. So those are the references. So let me crack on. So the model, we need a simplified model to explore these questions of network contagion. And the model I'm going to use is the SIR model of an epidemic. So SIR, as I'm sure you're all aware by now, stands for susceptible, infective, and recovered. So here's a tiny little piece of a network. The dots are going to be people, and the lines between the dots represent possible contagious contacts. In the simulation, we start with one initial infected individual, and I put the star by infected to remind me to tell you again that this applies to other models. So it could be an individual with a piece of information that they're spreading, or it could be some other thing, right, that's spreading in the network. So start with one initial spreader, and it can spread along the edges. So this infection may be passed along the edges of the network, and there's some kind of a delay. So it's not the case that you instantaneously get sick if one of your social contacts gets sick. There's an incubation period of the disease, then you have to meet them, and then there's a process by which you spend some time with them. So after some delay, you might become infectious yourself. Now that delay is random. It's random in the sense that it's unpredictable. So we model it as a random variable, big X, and it has a density function, little f. Infected nodes can recover, and we model this by allowing big X to be infinity. So sometimes the delay between one person getting infected and me getting infected is infinite because they don't manage to achieve infectious contact with me. So if the total integral of this density is less than 1, then that's saying that some of these contacts are simply never going to be infectious because that person recovers before they infect me. So maybe another infection takes place, maybe another recovery, and now the disease can't progress anymore because even though there's still active infections in the network, there isn't a clear path to a susceptible node, and you can't reinfect somebody. So this isn't Omicron that's coming back again. This is a kind of an emergent infection that confers immunity after you've had it. So the only thing left to happen is for the disease to die out, and then this is the final state. So one person didn't get it, and all of these other 3 did. So how do we quantify the kind of risk or the dangerousness of this disease? So in the epidemiology literature, we use this quantity called transmissibility. So this is basically the probability for an infectious node to pass the disease to a neighbor. So I have an infectious contact, they have the disease, what's the chance that I catch it at all at any point? So that's just this quantity big T, which is the total integral of the delay distribution. And if that's less than 1, that means that there's a chance that the delay is infinite. That's a chance we never spread at all. So big T is some number in the range 0 to 1. And this quantity is super important because if it's small, then the disease is going to die out really quickly. If there's a low chance of it spreading, then if a few people are infected, there's a minor outbreak and then it dies out. If it's large, then it could spread through the whole network. So here's a little example. So here's some sort of social network, let's say, and this is the initial infected individual, and we've got a high transmissibility. So as this disease progresses, it's going to spread quite rapidly through the network and leaving behind this kind of core of people who have had the infection, and only a few are going to escape with a high transmissibility. Now, this is sort of one random instance. You could think of repeating this as a simulation model several times, or you could think of it as saying, you know, what's the probability of each of these individual nodes getting infected at some point? If we now try again with a lower transmissibility, then there's going to be less successful transmissions, and probably the disease is going to die out quite quickly without managing to infect a bulk of the network. And there's going to be a regime shift between these two. We call it a phase transition. So for low transmissibility, you get tiny little outbreaks, and then suddenly there's going to be a point where large macro scale outbreaks become possible. So these are the kind of questions I have about this process. So what's the critical value or threshold for transmissibility in a given network? So can we kind of classify a network as to how infectious a disease has to be in order to spread on it? Which nodes are most likely to be infected? How fast does the epidemic spread, and which nodes will be infected first? So I'd really like to dig into this structure and say not just a network level property of how likely is an outbreak, but I want to say, okay, these 5 nodes are the key ones that are most at risk. They're likely to get it first. They're the ones we should watch or protect or invest some resources in somehow. And I'm going to use some applied maths to try and get at this. And the method is called message passing. And message passing is
sorry,
essentially.
Tim, can I just have a clarification? Was I missing something in your transmissibility function? I mean, shouldn't you not have had a weighted adjacency matrix and a summation sign? I mean, FXDX would not do it, would it?
So an alternative, an equivalent alternative would be to write down weights on the edges and then say only those edges whose weight is above some threshold are infectious. That would be absolutely equivalent. That's called a percolation process. The kind of difference in terms of, although mathematically they're the same, there's a slight difference in how you think about it, because the weighted edge version you think of as there's kind of one event, which is writing all the weights and then deleting the edges, and then you look and see what's left. Whereas in this kind of spreading picture, I'm thinking each time I encounter an edge, I decide how long I wait before I
So that is common, global. This transmissibility rate is global to everybody, is it?
T is a fixed parameter that's the same for everybody. I mean, in this model,
right.
you could make it different for different people, and if you wanted to sort of, there's various kind of fine tuning and more realistic things you could add. One of which would be this, but for the sake of this work, I'm going to keep it fixed for everybody. Okay. So I'm conscious already of time. There is going to be a wash of equations coming. But I've put the links for the papers. So I'm going to blast through the maths quite quickly. And if anybody wants to look at the detail, you know where to find it. So here's the idea. We're going to define a system of random variables that tells us the information we want from this model. So for all nodes, I'm going to have nodes I and nodes j. So Ti is going to be the infection time of node I. And I'm going to call that Ti equals infinity in the case that node I is never infected. So if it's a finite number, it's when it got infected. If it's infinity, that means it never got infected. And then T and I'm going to use this notation that has a subscript I from j, that's the time that node j has infectious contact with node I. And again, I'm going to use infinity in the case that no such infectious contact takes place. So that subscript is telling you the direction of the transmission of the disease, okay? So these are random times. And then one more thing, big X is going to be the delay time. So it's the delay between node J being infected and it successfully passing it to a neighbor I. Okay? So when I receive the disease, for each of my neighbors, I wait a random amount of time before I transmit to them. And for some of them, I wait infinitely long. And they never receive it. So these are my random variables. And I now need to figure out the relationship between them that's described by the network. And it works as follows. So Ti, this is the time that node I gets infected. And that's just the minimum of the times that its neighbors had infectious contact with it. So the time that I'm infected is the first time somebody infectious has infectious contact with me. So this is kind of obvious. The next one is a little less obvious. So what is the first time that somebody has, that node J has infectious contact with node I? Well, first of all, node J has to receive the infection from somewhere else in the network. So I look at the minimum over the other nodes, K, who are neighbors with J, but that are not I, of when did they have infectious contact with J. That's J receiving the infection, and then it has to pass it on. So then I add on this random delay, X. So here I'm looking at the event that K gets sick, passes it to J, and then J passes it to I. Okay, so this now is a system of equations that relates a bunch of random variables on a network. So as these are written, these are relationships between random variables. I'd now like to translate them into relationships between the density functions for those random variables. And then I can start doing analysis. So let's let capital F, this is going to be the probability of node I being infected before time t. And similarly, Fi from j is the probability that the transmission event happened before t. Now, I'm going to make a crucial assumption of independence, which is not technically true, but it turns out to be good enough that we get really, really good results on most networks. So it's going to work for us for now. So we can work out, what's the relationship described by this. So this equation is about random variables, and then this is the corresponding equation for the density of those random variables. And then the same thing happens when we look at the transmission events. It's a bit more complicated because we're not just taking a minimum, we have to add on something. So we end up with a convolution integral over the delay period. So this is the full equation. This is called the message passing equation that describes the relationship between when do I think J had infectious contact with K and compare that with when do I think I had infectious contact with J. So this now is a system of equations that relates functions that live on the edges of a graph, right? So I've got a large network, so I've got lots of edges, and on those edges I've got these functions, and they relate to each other according to this equation or this system of equations. So ideally, I now need to try and solve this system. So these, as I said, these are called the message passing equations. In other literature, they're sometimes called the cavity method or belief propagation. So belief propagation comes from the idea that node J might have some information that it's transmitting to node I, and this equation is about how you integrate the information you get from different sources and then pass it on. All right, so how are we going to solve this? So firstly, let's simplify things a little bit and just look at the case of, are you infected eventually? So it doesn't matter when it happened, just whether it happened or not. So for that case, I'm going to set little t to be infinity, and I'm only interested in computing something I'm going to call the riskiness of a node, so Ri. So this is just Fi of infinity, meaning did I receive the infection before time infinity? So did I get it at all? And then this relates to the neighbors as follows. So this equation, by the way, you can read again and check that it works with your intuition. So this says, what's the probability of node I being infected? Well, it's 1 minus the probability that it's not infected. And for it not to be infected, it needs to have failed to be infected by each of its neighbors. So the product means all of the neighbors have to fail, and then this is the probability of their failure. And then for these guys, we can do the same thing. We plug it into the more complicated equation. The integral now, because it goes to infinity, I'm not worried about the full shape of little f. I'm only interested in big T. I end up with this algebraic system. So this tells me how the riskiness of an edge between the 2 nodes relates to the riskiness of the other edges that are incident on that edge. So this is a non-linear system of equations, but if I can solve it, then I can make predictions about where is at risk in this network. So there's a general procedure then we can outline. So you've got some disease. So step number 1, you compute the transmissibility by doing this integral. Step number 2, you solve this system of equations. And step number 3, you plug it in here to deduce the node risk. Now, I've said this is easy, but it's not super easy because this step here is, this is a large non-linear system. So pretty much numerical solution is the only option we've got. Luckily, you can just iterate. Now, in order to do this iteration, I'm going to have to introduce another network object, which turns out already exists in the literature. It's something called a non-backtracking graph, or a Hashimoto graph, because it showed up in number theory back in the early 90s, and then was kind of rediscovered in this network setting quite recently. So this is the graph that describes the relationships between the messages in this message passing process. So its nodes are ordered pairs of nodes in the underlying graph, and its edges. So I draw an edge between the pair LK to the pair JI if K is J and L is not I. Now, usually when something like this crops up, I try and draw a picture so I can understand it better. But actually, that's not very helpful in this case, as you'll see. So if I draw a super simple little graph like this, if I then draw the Hashimoto graph on top, I end up with a horrible sort of spidery mess. But I can describe what's happening here. So this black network is the Hashimoto graph of these relationships between these variables. And so each edge in the underlying graph spawns 2 nodes in this new Hashimoto one for each direction that you could walk down it. And then I join them up if it's possible to walk down one edge and then the other one without turning around. So there's a line from here to here because it's possible to traverse this pathway and then this pathway without going backwards. So that's all it is.
So just the intuition of the non-backtracking. So you're saying, wouldn't other people call it sort of acyclical, or are there not other ways in which we could understand this?
It's not necessarily acyclical. It may have longer cycles, but it's removing the very short cycles. The intuition for why this is an important object is quite simple, because if I catch the disease from my wife, then she probably didn't catch it from me. So the path that the disease has taken through the network is non-backtracking. And the same follows for information flow, and the same for credit contagion, and a whole bunch of processes.
Yeah, that's very interesting. This sort of has applications in finance, doesn't it? I mean,
exactly. So anytime you have this kind of immediate non-reciprocity, then it's probably not the adjacency matrix you should be thinking of. It's probably this Hashimoto matrix.
Very interesting.
So yeah, that's the big takeaway from this whole talk.
Yeah, that's very interesting.
Thank you for pointing that out. Okay.
Is it like this directed acyclic graph, or no? There will be there can be possibly cycles.
There will be cycles. You can probably spot one in here if you chase it around long enough.
But it has a causal interpretation. I think that is the takeaway.
Exactly. Yeah.
Okay,
but I think the other crucial element is that the cycles are long. So usually they traverse a large part of the network before you eventually come back to you. And in fact, they turn out to be long enough that they're not terribly important in the analysis, which is a very helpful feature.
Thank you.
Okay. So written in terms of this Hashimoto matrix, my nonlinear system has a slightly simpler form. I can think of a map that basically, so on each edge for each direction, I have a guess of what I think the risk is, and then I can update it according to this map that integrates each of the risks coming in and then gives me a new number here. So solving the message pass equations is basically finding a fixed point, and that also then gives us a way of getting at things like stability, because we can examine the stability of fixed points and so on to decide on the different solution regimes. So as I've described, simple iteration still works. And right, here's the key picture. So this is a typical kind of result you get from analyzing risk in a standard kind of randomly generated network. So here I've got a network with something like 500 or 1,000 nodes, and I've considered various different values for this transmission parameter t. And for each of those, I've calculated for each node what is its risk. And those are these little gray lines here. So every node has its own little profile that describes how its risk increases, risk of getting the infection increases as the transmissibility gets higher. So the things that stand out in this picture are firstly this threshold down here, that there's this special value below which risk is basically zero, and then suddenly it explodes. And then the other key thing is that these paths are not kind of neatly layered. They can cross over each other. So I've picked out two that I then did some simulations to sort of double check. So the purple dashed one and the green solid one. So this pair is a pair that reverse their ranking of risk. So the green is more at risk than the purple when t is quite low, but then they switch over for t quite high. So there's some kind of complicated process going on here that describes how is risk apportioned in these networks, and it's different for large T and for low T. So I'm looking at time. I've only got a quarter of an hour. I'm not going to show you how I did it. You'll have to read the paper to find out how. I'm going to blast through these slides, but I'm going to answer these questions about the epidemic threshold and the rank order of risk. And it's all to do with stability of that system. So let's go away. It's a basic stability analysis. And here is the answer. You end up eventually with a linear equation that says take your matrix B that corresponds to the adjacency matrix of that Hashimoto graph I showed you, the non-backtracking graph. So write that non-backtracking graph as a matrix, look at that matrix, find its largest eigenvalue, and that is 1 over the critical transmission threshold. So that matrix contains crucial information about how transmissible a disease has to be in order to spread in this network. And moreover, the ranking of risk comes from the dominant eigenvector of that matrix. So the risk associated.
So we're back in very familiar territory then.
Right, exactly. So it's all eventually eigenvalues and eigenvectors. So you compute this top eigenvector, and that tells you for each one of these nodes sort of who is relatively most at risk, and the behavior is linear near that transition point.
So just a quick question. Isn't it then the convergence of Markov chain result, basically, that it will converge to the dominant eigenvector?
There's not necessarily Markov chain underpinning this. It's more that there's a collection of functions that are related to each other in this nonlinear way. I can iterate an algorithm to find the solution, and it's about the stability of that solution.
I see.
Okay, and then up the other end. In the other end, things are actually more simple. It's all about how many neighbors you have. So Taylor expanding around certain transmission, you only get a non-zero coefficient in the expansion at the order of the number of neighbors you've got. So what that basically says is every extra contact is a proportional extra chance to become infected in the highly infectious regime. So returning to this picture, I can answer those questions. This point here is 1 over the largest eigenvalue of the non-backtracking matrix. Each of the lines is leaving as a straight line from that point, and the slope is given by the corresponding entry of the eigenvector. And then up this end, the paths separate into bands And your band is decided by what degree you have as a node in the network. Okay, so that's answering all the static questions. I promised you stuff about speed. I've got about 10 minutes, I think. So I'm going to go nice and quickly through speed. So how do we make that analysis that was all about the static situation? How do we now answer the questions of how fast it's going to spread and who's going to get it first? So we need to, at some point, I derived these equations relating the time of infection, and then I put t to infinity because I was only interested in the endpoint. But now I need to roll that back and think about general times. And now the exact shape of the distribution of delays is going to become important again. So this is my equation. I'm augmenting it with a superscript of n, because I'd like to think, how far am I from the source in terms of steps in the network? So big F, j from I, n, t is going to be the probability that node j has not transmitted to the infection to I before time t, given that the initial infection was n steps away in the network. And I can relate that then to what happens when the initial infection is only n-1 steps away. So this is a bit like saying, okay, I'm personally worried about catching the disease. So what I'm going to do is I'm going to survey all of my friends and family and work out how close they are to their friends and family, to their friends and family. I'm going to chase it all the way backwards until I find the source. And now I can think about the possible pathways that the disease might take. And this is one step of that chasing process, is how do I go from distance n to n-1, so closer to the source. When you calculate these things for standard or simple networks, this is the kind of picture you see. So if you're at distance 1 from the source, you're just waiting to have it transmitted to you. And this blue curve describes how long you're going to have to wait. If you're at distance 2, you have to wait for that first transmission event, and then you have to wait for it to be transmitted to you from one of your immediate neighbors. And you get a slightly different curve, and 3, and 4, and 5, and 6. And eventually, the shape stops changing. And eventually, it settles down to a constant sort of shape of a function that's just shifted right by a small amount, tau. So this tau is the typical delay between one person at distance 100, say, receiving the infection, and then passing it on to somebody at distance 101. So the typical delay between layers 100 and 101 is about the same as the typical delay between layer 1000 and 1001. And the shape is basically the same. It settles down after a while. So what I'd like to do is calculate what's that shape and what's this delay tau.
Sorry, what was on the x-axis?
Is time. Oh, it's cropped. Sorry, it's time. So it's just saying the probability of infection prior to a certain time. So the longer you wait, infection gets more likely. But the further you are from the network, the more you're going to have to wait for it to reach near you and then for you to get it.
So time, I mean, so what is 2.5 then?
Arbitrary units. These are units. Actually, no, I can tell you the units. It's units of typical infectious period. So the blue curve here is the easiest one to think about. It's just the mean of when it was transmitted. That'll be 1. But these are so that would be how we measure time, basically. Okay. So I'm going to again approach it from a linear point of view. And the linearity is only present in one particular regime, which is when we think about very fast transmission. So what's the possible probability that I am infected very early on in the epidemic? Well, if I'm going to get the disease unusually early, I only need one of my neighbors to have got it unusually early. So there's an additive linear effect there, that every extra neighbor that I have is another chance for me to get it unusually early. So that thinking about sort of these early times allows us to take this piece here and to linearize it when f is very small. So that's going to become that product, that messy nonlinear thing is going to become a sum, which is starting to get nicer. We still have to deal with this integral, and we're going to do that with a Laplace transform. So if I've got any engineering student knows, if you've got a sort of convolution integral like this, if you Laplace transform it, you end up with something nice and multiplicative. And now we're back in linear land, right? I've got another linear system involving the non-backtracking matrix. This sum here is the sum over the neighbors in the non-backtracking matrix. This f tiddle s, this is the Laplace transform of the delay distribution. This is how the characteristic of the disease feeds into the spreading time. And then this piece here is again this linearity coming from non-backtracking. So what do we expect? Well, we expect to see exponential growth. And then we can, if we plug that in as an ansatz and solve, then indeed we find a formula that tells us what our typical delay is. It's non-intuitive. It's a maximum over a difference of logarithms. It's a weird sort of thing. You have to do quite a bit of work. I've condensed it in this slide. You have to do quite a bit of work to get this, but it turns out to work beautifully. So here is our predictions of different speeds in different networks. So each dot here is representing a network that we've downloaded from this Snap database that we then run a bunch of simulations of epidemics on. We've calculated the typical spreading speed, and we've compared that to our linear theory for this delay, and we find this nice correspondence. So we actually get a very accurate prediction for the speed of spread, or the typical delay in the layers as you spread through the network. It also lets us
so Tim, remember you said the speed is something to do with the distances in the network. So I'm again a bit lost here. What is tau?
Right, so tau is delay. So tau is 1 over speed.
Oh,
so
yeah.
Tau is the delay. So 1 over tau is the speed.
So somehow you calculated these distances in the network. By that I mean I understand distance in the network. I mean the first people who are one removed from me.
Unit 1, Unit 2,
yeah. So those are what you mean. So you have the path lengths, right?
Yeah. So basically, I'm
just
saying
the path lengths.
Not quite the path length. It's saying if a node has a path of length 10 to the source, then the time I expect it to be infected is 10 tau.
Okay.
So tau is how long I expect to take the disease to spread over one distance. Okay. This is showing you how tau can vary with the properties of the disease itself. So the time in the delay to spreading. And basically the message here is that having an infectious period that's tightly concentrated around a typical value leads to slower spreading than having an infectious period that can be very large or very small. It's really the anomalously small events that determine the overall speed of spread. And I'll blast through this, but another final result then is when, who is going to get it first. And again, it turns out to be exactly the same result as for risk, only it's a log linear relationship. So I previously showed you how you could calculate a guess, sort of not a guess, a kind of a number that codifies the risk of a particular vertex. Turns out if you take the log of that number, that'll give you a very good prediction of when in the disease, in the epidemic outbreak, is that node going to get the disease. So these are a bunch of simulations from a bunch of different types of networks, always showing this log linear relationship between this centrality quantity that we compute and the time to infection. Lastly, one final sort of interesting feature from this. So this relationship that I showed you here about the log linear relationship between risk and infection time. Risk is something that we calculate as a purely local property. It doesn't know how big the network is. It's all to do with just an eigenvector, and it doesn't have any clue about how large the overall network is. So what that means is that if you think about larger and larger networks, so your social network going all the way up to the scale of the whole world, the calculation of risk isn't going to change, and therefore its logarithm isn't going to change, and therefore the expected time until you get sick isn't going to change. So what that means is that we expect a very explosive epidemic spread process. We expect a slow start and then a very sudden period, a short period of time in which it spreads through almost all of the network, and then a slow sort of mop up at the end. So this is kind of bad news in a sense, because it says that, you know, if you watch an outbreak on a time scale that lets you see the start and the finish, it means that almost all the infections happen in a very tiny window of time right in the middle. There's a real danger period right in the middle. Okay, I'm going to wrap up. These are the summary of what we figured out. So first important question, what is this epidemic threshold for a particular network? Well, we find it's the reciprocal of this non-backtracking matrix, of the top eigenvalue of the non-backtracking matrix. What are the risk profiles of the individual vertices? Well, that's proportional to this non-backtracking centrality, which is this top eigenvector of this Hashimoto matrix. That's for low risk, for low transmission. For high transmission, it's basically just degree. And then on to speed of infection, we have this strange looking formula that does a good job of predicting how fast an epidemic can spread through a particular network. And that marries properties of the disease, this is the delay time, with properties of the network itself, and how the two things combine to set this delay time. And then finally, when is my personal expected time to receive the infection? Well, it's proportional to the log of my non-backtracking centrality. So just to very finally finish, I want to sort of issue a sort of warning for all of this research. I'm not 100% convinced that it's something that we want. This is a news story from early on in COVID, where South Korea, if I remember correctly, had a very stringent track and trace process that was also quite public. I think they were releasing a lot of information about where people had been, so on and so forth. They were really putting effort into putting together these networks and then using them to predict who ought to be tested, who ought to isolate, etc., etc. And this made a lot of news around the world, not because it was a marvelous way of stopping the disease, but because it had questions about people's privacy and liberty and so on and so forth. And so I want to sort of caution that all this personalized, this is very interesting from a mathematical point of view, but is personalized predictions of this sort of thing really the direction we want to take? I'm not sure. So that's it. Thank you. I'm very happy to take questions, although I'll be eating into the next speaker's time. So maybe we should make it very brief.
Just very quickly, Tim, that is very fascinating. Maybe the thing that I've learned is about your Hashimoto matrix. Now, if you weren't using one of those matrices, how would it be different? Because all the results look very familiar to me, on your last but one slide, that one, yeah.
So I've mentioned a couple of times this thing, non-backtracking centrality. Yeah. That's the name in the literature for this top eigenvector. That was invented first, nothing to do with epidemics. It was invented as just another nice metric you could calculate, and it was supposed to fix a problem. And the problem it was
number theory, you said.
Well, no, when it first came to the network science literature. It was supposed to fix a problem, and the problem is that most of the kind of first attempt of metrics that you decide to put on a network, they get very heavily concentrated on high degree vertices and on neighbors of high degree vertices, and you get real sort of almost not useful results sometimes, with these high degree vertices. This was designed to counteract that. And that's the kind of key difference is that, so firstly, what I've shown you here is a principled derivation that is correct in a certain limit, right? Secondly, if you compared it to another measure, just like a pure eigenvector centrality or something, you would get the wrong answer. And the reason you would get it wrong is because it would be putting too much weight on high degree vertices and cliques and things like that. Essentially because it wouldn't be ruling out transmission, back and forth among neighbors many times.
It's very interesting. Yeah. So So that's very valuable. There's many of us who work on financial networks, and I really think we should look into this.
Right, exactly.
Yeah, that's brilliant, Tim. That's my questions done.
I think I can see is. Do we have time for one more?
Yeah, the question from Nick Forrest. If I said that right.
Thank you very much, Tim. It's absolutely very, very, very interesting. I'm not a mathematician, so I apologize if I've missed something along the line. But I was wondering, in cases where people are not so structurally sort of well-defined within the network, I'm thinking, I'll just give you an example. I was, at the beginning of the epidemic, I was working in Leicester, but live in London and commuting between the two. And say Leicester was a sort of hotspot at the time. So I'm just wondering whether you would model it as something within the parameters when you particularly sort of looking at the edges, because I'm obviously sort of 2 times a week sort of going backwards and forwards. I'm on a train. I'm going to my family where my wife is actually just living in the house and not going anywhere. But I'm just wondering whether you would see it as kind of 2 separate networks, which with some people basically acting as links between the network model that you've set up, or whether it's built in to the actual parameters. So I apologize if I missed that.
No, that's
and just the second one was with the belief propagation. I'm thinking that would probably work with things like spread of ideas, fake news, sentiment. Also, even I don't know, perceptions of an innovation. Things like that. So just an interesting kind of aside there.
Oh yeah. So on your second question, the answer is yes, absolutely, and there's lots of research in that direction. On the first question, it's a very valid point. I think the short answer is to say that in the work I've presented, the network is considered as being static and or at least changing very slowly with respect to the timescale of the disease. So it might be a better model of information rather than necessarily of an epidemic. What you're raising about how contact networks change in time is super duper important, and is a really interesting challenge. For me, all I'll say is I've looked into it, and really interestingly, all of this stuff breaks, and it should work perfectly. And it's really interesting that it breaks. And the reason it breaks is because the process I described about sort of iterating, where you look further and further away in the network, when you think about a network that changes in time, you're also looking further back in time. And eventually you reach the beginning of time. And what was there? There was no network there. And then the propagation process fails. And so we really, it's quite interesting. It turns out that it's going to need some fundamentally new ideas, I think, actually. And that this mathematics as it stands won't work on its own. We need some new theory there. And I don't know what that new theory is, but I have devoted a lot of time to it. So hopefully I can come back in another 7 years and tell you.
It's really, really interesting. No, I think it's a super area. Yeah, absolutely. I'm very fascinated.
Cool. Thank you.